Hello, today I want to continue my previous video. In my previous video, I discussed about a full swath model. It's here, full swath 2D or full shallow water equation for overland flows. And as you can see, this 2D. It means a two-dimensional model, two-dimensional numerical model. And actually, there are two model in here, physics informative neural network and the full swath. Now I want to focus in the physics informative neural network. So in my previous video, we successfully create a output. One of the output is whose final dot dot and whose evolution dot dot. For the whose final dot dot, it contains the last state of the last state or the last time step of the model. If you want to see the evolution of the parameter, you can check the hash evolution. And actually, the time step in here I set the time step for every 1 second. You can set that in the parameters. You can set that in the parameters.txt. In here, number of times 7, because we have a final times 50, and then the number times of 7 is also 50. Then automatically the time step in here will be 1 second. So I plan to input this to the pin model. So before that, we must convert this to the something that the Python can read, right? So that's why I create this script. This is the script to convert the GNO plot file to the NPZ file. NPZ file is a array that have multiple parameters inside that. And then we move out to the model. So here, this is the class of the model that we use, and as you can see here, there's nothing peculiar in here, except here we have this self.n and self of bed slope coefficient. So actually, I will explain this later. This is the same. This is where we initiate the model, initiate the linear layer and the activation function. Here the activation function we use is tangen hyperbolic. Oh, this is the interesting part. So actually, in every paper that using a physical informative neural network, usually they will initiate the weight and bias using the Xavier normal like this, and then the bias will be initiated as zeros. And as you can see here if the tangent hyperbolic is only applied to the last two layer, that means the output layer will not have the tangent hyperbolic. So the final operation is just a linear operation. This is the physics laws. Oh, before that, I want to explain the equation before I move to this. So actually, in the original paper, they say they using the full swath two-dimensional model. So actually, this full swath is two-dimensional, but I found the equation that they use is just one-dimensional, because they only derived the velocity in here just 2x, and also the velocity in here just u. There's no v. So that's why I conclude that they only simulate the one-dimensional runoff model, and in this experiment I will simulate two-dimensional model. So I think this is will be maybe this is will be more advanced than this paper, but actually in this paper they simulate multiple yeah, they simulate multiple simulation, but in my experiment in here I only simulate one simulation. So yeah. Okay, this is okay. Actually, yeah, I say this is one dimensional, but if we want to use if we want to simulate the two-dimensional model, then we must expand this equation. So we will have the additional term in here like this. Actually I forgot to write the equation, so maybe when I edit this video I will show you the full equation that I use. Okay, here this is the physics laws. So first we input the clone to play it safe, and then here I use the model. So as you can see here, the physics laws is in here. One of the parameter is the model that we use. Here here we run the model and we got the output, and actually the output of the model is three. There's three parameter. One is the h in here is the water depth, the u in here is the velocity in u direction, and v also the velocity but in the v direction, you know, the south north and west east, yeah, direction like that. And in here we clamp the value of h. It's nearly 0, but actually it's not 0. Why I do that? Because in here we must power the h by 4 per 3. If the value of the h is minus, then the value from this operation will be none, and then the entire operation will in here will be none, and then we get the loss of none, and it will trigger an error. So that's why we do this. And then after that, here we try to derive the u, v, and h to t, x, and y. And then here this is the friction term, as you can see here. This is the term that we code here. So in the paper, this is only in the original paper we only do that in the x direction, but because we simulate it in this is in two-dimensional simulation, then there will be sfx and sfy like that. And then here this is the PDE for u and PDE for v. Oh, and actually here there's two constant that is written in this paper. One is Manning coefficient, and then Manning coefficient as n, and then the friction term. I don't know the value of this, so that's why I create additional parameter in the spin model like this. Actually, the bed slope coef in here is just the coefficient that I create by myself, because I found that if we include these two terms, it will introduce us to additional error. I will show you. Okay, so actually this is just a script. It's just to prove how reliable the fiscal laws that I use in the original script in here, because I want to prove how reliable the fiscal loss function that I use in the original script. That's why in here, because we don't use any model, then the derivative we got is from the finite difference. We use the original ground truth data. And as you can see here, big error from we got a big error for the total PDE. And as you can see here, the biggest contributor of the error is from the U and V. It's not so much. It's I think this is forgivable. I think this value is acceptable, so H is passed, but not for U and V. And as you can see here, for the PDE, U, and V, it include this term, right? But for H, it's not include this. The source of the error is these two terms. So that's why if we comment out them like this, and as you can see here, the error is drastically decreased. But I'm still skeptic because as you can see here, I think we still need this term. So that's why in the original script in here, I just make the additional parameter like this. So how it's work? So the batch loss coef in here, if this term here, if this term is not important for the calculation of the model, then the coefficient for the batch loss will be 0. But if this is important, then I think the batch loss coefficient will be, we will have a value it's above 0, or we will have a bigger value. The more important this term, then the more bigger the value of the batch loss coefficient. So that's why even if we include this term that introduces us to error in the test of the PDE, it's still safe because all of this will be handled automatically by the neural network. And then here the PDE for H, and this is the total PDE. And this is just setting for the full swap model. In my previous video, I said that the width is 32 and the height is 64. And here I read the topography. So the topography is one of the parameters that I use for the runoff, for this runoff pin model. And for this is the X and Y coordinate. So actually different with ordinary neural network that you find in another paper. Usually when we have the parameter like X, Y, or time that is go beyond infinity, if you read another neural network in another paper, usually when they handle X or Y coordinate or time, they will try to do a positional encoding, but in here they not. So I just follow the previous paper that using pin. So I think that is because the output of the model will be processed by this physical loss. So if we doing the positional encoding, then the this derivative from them will be invalid. Actually, all of this line is just to create the dataset. This is where I create the tensor dataset and then define the data loader. And then this is the part where I define the loss, the ordinary loss function. Here I'm using min. For the optimizer I'm using Adam. And airports, actually in few article and paper that I found, usually they will be using a very big value for epochs. I don't know why, so I just follow them. And then in here, this is just the mechanism to save the base model. And here this is just the process to produce the prediction. Here this is the ordinary loss, and here this is the physical loss. So the total loss is ordinary loss plus physical loss, and then after that we doing backward and doing optimizer step. And then this is just to log the error. And here we save, I already explained about this, we save the base model when we found the current loss, when we found the current lowest loss. And in here, this is the final save of the model. So actually, if I run this, it will take a long time, so I will just show you the result here. Pin model discovery base, and I am using this to run this runoff predict. So in here I run the model, and then in this script we try to create a GNU plot file. Here we have two GNU plot file, one for the prediction and one for the label. The file is like this, so it's just a bunch of number. So to make a sense of it, of course we will do the GNU plot file. We do it like this, GNU plot, and then GNU plot anim model, enter, and we will get, this is the result that we got, and this is the label. And as you can see here, it's quite similar, right? And actually when I run this runoff predict, I'm still not satisfied, because in here we only predict one time step ahead. So for the prediction time, for example here, prediction time step 1, it will depend on the truth data of time step 0, and for the time step 2, it will depend on the ground truth data of time step 1. What I want to do in here is I want to completely replace the original full swap model using this pin model. So that's why I create the third script. In here we doing a loop back fit model, so the output of the model will become the input for the second run. So in here we try to predict for 50 time step ahead. So we will run it like this. Wait, Actually, I don't want to run it, but because it will ruin my result, so I will just show you the result. So the result, it will be something like this. And actually, I quite satisfied with this result because uh, because as you can see here, the movement of the prediction in here is quite natural. It's because the runoff pin model that I built here is already comply with the continuity equation or the physical laws that we use. So that's why even we even we doing the loop back fit model, usually if we using the ordinary neural network, the result will be quite unnatural. And I think that's all. Okay, bye.